I'm Matt Fillingham, so I'm an astronomy instructor here at Berkeley City College. Thank you. But it is my distinct pleasure to introduce tonight's speaker. Dr. Turi Hiller is the research scientist at NASA Ames Research Center, so just down the road. He's worked there in some capacity or another since about 1998 in the exobiology branch of the Space Science and Astrobiology Division, which sounds fascinating. He's also part of the Virtual Planetary Laboratory, which is headed out of the University of Washington. It's one of the oldest, that I learned tonight, NASA Astrobiology Institutes. So that's pretty cool, too. Let's see. I have a lot of information here. So before he started working at NASA, he received his degrees from the University of North Carolina in chemistry and marine chemistry. And much of the research focuses on how life interacts chemically with the environment. So I'm sure I'll talk a lot about that tonight. I was also part of the Mars Science Laboratory. That's the Curiosity rover, the science team. I was part of the science definition team for mission to Europa, which is, if you've taken my class, you know it's a fascinating place with good stuff happening. Let's see. I've also been honored many times for his research. So he's a fellow of the California Academy of Sciences. Was a Kavli Frontiers of Science Fellow also. Let's see, received award for excellence in research at NASA Ames. And also had the honor of giving the Carl Sagan Lecture at the American Geophysical Union meeting, which is a pretty high honor, I think. Also on the editorial board of several scientific journals covering topics like astrobiology, geobiology, and microbiology. So maybe you note a theme there in the biology aspect. Also gives many public lectures like tonight, so we're very happy he's here. And last thing I want to say is also a consultant advisor for radio and big screen. And so he worked on, and was actually in the IMAX documentary, Aliens of the Deep. So there's much more I could say, but he's supposed to give tonight's talk, so I'll turn it over to Dr. Turi Hiller.
So thank you all very much for coming. Doing this sort of thing is actually one of my very favorite parts of my job because it helps me kind of remember what gets me excited about it in the first place, and I hope that I can convey some of that excitement to you guys. This topic is really exploding in astronomy and biology right now, and I'll try to tell you a little bit about what's going on. You know, as Matt told you, I'm a chemist, and this is a talk about astronomy and biology, so maybe that should temper your expectations a little bit for what you're going to hear. But actually, for me, chemistry is the language held in common between those two things, and ultimately, if we're going to do this job right, it's going to require not just astronomers, but geologists and geophysicists and biologists and a whole spectrum of people in order to understand the places that we're looking at. And I hope that I'll explain in the course of the lecture a little bit why that is. So, and actually in that spirit, I have just myself listed up here, but I reached out to a whole bunch of friends of mine who represent different disciplines across that spectrum for materials in the talk that will hopefully bring it alive for you. So Natalie Battaglia is the mission scientist for the Kepler mission that's discovered a lot of the exoplanets we're going to talk about. She and the whole Kepler group do a really amazing job of visualizing their data and making it sort of understandable and visual to people. Jeremy Kasdan is one of the people designing the next generation of telescopes that will hopefully actually let us visualize some of these extrasolar planets. Scott Sanford and Nikki Peranto are colleagues of mine at Ames. They gave me some of the chemistry data that I will torture you with a little bit later. And as Matt mentioned, I'm part of the Virtual Planetary Lab. So Virtual Planetary Lab is a group led by Victoria Meadows that has sort of dedicated itself to understanding the scientific context around exoplanets. And I'll explain a little bit what I mean by that later. But the question, are we alone in the universe, is by no means a new one. We're certainly not the first to ask that. And actually the title, Innumerable Globes Like This One, that phrase is plucked from a 4 centuries old text written by this person, Giordano Bruno. He was a Dominican friar. He wrote 400 years ago what I consider to be a remarkably foresightful set of observations, predictions, call them what you will, and I'll read them to you, but just for context, so Bruno wrote this text, as I say, about 400 years ago. That was maybe 40 years after Copernicus told the world that the Earth revolved around the sun and not the other way around. So news traveled slowly then, but people were kind of aware of this idea. But it was still a good 25 years before Galileo would make the first telescopic observations. So to the people at that time, planets were just points of light that behaved a little bit differently. They weren't things that you could actually see and resolve through a telescope yet. And considering that that is true, considering that that's where things stood, to me, it's really remarkable to hear what Bruno had to say. He said, there are countless suns and countless Earths, all rotating around their sun in exactly the same way as the 7 planets of our system. There were only 7 then. We didn't have Uranus, Neptune, or Pluto, and we lost Pluto along the way. We see only the suns because they're the largest bodies and are luminous, but their planets remain invisible to us because they're smaller and non-luminous. The countless worlds in the universe are no worse and no less inhabited than our Earth. Right? This is kind of a remarkable set of predictions considering when they were made. Unfortunately, the world at that time was a different place, and ideas like that were not appreciated as much as they are now. So this statue of Bruno actually stands in the square where he was executed for heresy. It was a less popular way to think than it is now. We live in a different time, though, and in fact, we have begun to enumerate those countless worlds and countless globes. So we know that just within our own galaxy, there are hundreds of billions of stars. There are something like 70 billion trillion stars in the observable universe. Right? We know there are many, many stars out there, and we're beginning to count the worlds as well. So beginning about a quarter century ago, we could begin to attack this statement or address this statement of Bruno's that there are countless suns and countless Earths. So what you're seeing here is a plot of the pace of exoplanet discovery through time. And what I want you to do is watch the pattern. So right now we're at about the time I got to NASA Ames, 1998. There were 2 exoplanets known orbiting around main sequence stars. So watch what happens as time goes along to bring us up to 2015. The pace of discovery is really almost exponential. And what I want you to pay attention to, so each of the different colors in the bars there represent different methods of finding planets. So that plot is really dominated by 2 things. It's dominated by the red color, radial velocity, and by the green color, transits. And as of the end of last year, there were about 2,000 known exoplanets, with another 3,000 or 4,000 strongly suspected. So in the time that I've been at NASA Ames, which is about 17 years, the number of planets known has gone up 1,000-fold. That's a remarkable pace of discovery, right? Really extraordinary. So we are beginning to enumerate the planets that are out there as well. The 2 main methods, so the red version, which is called radial velocity, and the green version, which is transit, I want to tell you just enough about them so you can understand the methodology and how we're finding these planets. So the first main one that came along was called radial velocity, right? And the idea is we think of planets as orbiting around their stars, but really they're orbiting around a common center of mass, which is not dead center in the star, it's actually a little bit outside. So if you look here, the notion is this is the star, this is the planet going around it, and the planet exerts some gravity on it. So if you've ever taken like a weight at the end of a string, a ball or something like this, and gone like this, your hand doesn't stay in exactly the same place. Your hand actually gets moved a little bit by the mass of the thing that's orbiting, right? That is something we can see if we look at a telescope. And what we actually see is more like the far panel. So we see the star moving away and moving toward us, and moving away and moving toward us. And the way we see that, if anyone's had the experience of listening to like a car horn or a train whistle as it approaches and then goes away, as it's approaching you, it sounds like a little higher pitch, and when it's leaving, it sounds like a little lower pitch. Right? Can you think about that experience? So we can actually see that with the light as well. When the star is moving toward us, we see its light compressed a little bit, and it looks a little bit bluer to us. And when it's moving away, it looks a little bit redder to us. Not a lot, because if you look at the influence of the Earth, for example, on the sun, that pull on the sun, it's about 1 meter per second. So literally, it's going about like this. Right? That's something we can see if we look with a sensitive enough telescope. And this is responsible for hundreds and hundreds of planet discoveries. And you could sort of imagine that the amount of the wobble that we see, right, we're much more sensitive when the planets are big and heavy because they exert a stronger gravitational pull on the star, right? So we'll have a better sensitivity to really big planets. And we'll have a better sensitivity to planets that are much closer in because they make the star wobble at a higher frequency, right? And it's much easier for us to pick out. So we can say by this how long it takes the planet to go around the star, and we can say something about its mass. We can actually put an upper limit on its mass. And we're most sensitive to big planets that are close in. So a handful of years ago, maybe 10 years ago, 8 years ago, NASA launched the Kepler mission. How many of you know about the Kepler mission at all? That's awesome. So here's the idea. If you look at our own sun, right, every once in a while, you'll see planet Venus, in this case, occasionally planet Mercury, actually transit across the face of the sun. You can see this sometimes, right? It happened a handful of years ago. If you wear the right kind of protective glasses, you can look with your own eyes and see a little dot of Venus go across the sun, right? This happens if there are planets orbiting around other stars that we're looking at. But what if you actually don't get to see the disk of the sun and the disk of Venus there, right? You can resolve that because you have spatial information. You can see the little disk. What if you only see the star as a point of light? Then what would you see? When the planet goes across the face of the sun, it dims the sun a tiny little bit, right? Just by the amount of shadow that that planet casts. And if you take the case of Venus and the sun, or Earth and the sun for that matter, Venus represents about 1/10,000th of the area of the sun, and that's how much the light of the star dims. So if you want to find planet Venus around our sun, you need to be sensitive to the dimming of the star by 1 part in 10,000. And they actually are, they're better than that, right? So if you watch, so here's a planet that's transiting across the face of a sun, and on the bottom there is a plot of brightness, how much light is coming from the star against time. And as the planet goes across, the light dims a little bit, right? And it stays low for as long as the planet takes to go across. And when it gets to the other side, the light starts to come back up. So you can watch and you can say several things if you stare at a patch of sky and look at a whole bunch of stars. And that's what Kepler did, actually looked at about 100,000 stars or so and just stared, right? Like sometimes I sit and look at the night sky and I look for shooting stars or things like that. I've got about 15 or 20 minutes in me before I get kind of bored and start doing other things. Kepler spent like 4 years staying there staring at exactly the same patch of sky, looking for these little dimmings of light, right? And you can say a couple of things. So if you watch and you see this happen once, and you wait a while and you see it happen again, and you wait a while longer and you see it happen again with exactly the same timing, you know you're seeing something periodic and regular happening, and you know how long the orbit of that planet is. So again, we can say something about the orbital period. In this case, we can also say how big the planet is, because we know how much the star is dimmed. We know what size the shadow of the transiting planet must be, and so we know the size of its disk. Okay? So I want to show you the same kind of information, the pace of exoplanet discovery, but this time in a different way. So now I've plotted this, and on the bottom axis is orbital period, because that's something we can say from both of these methods. And on the top, on the y-axis, is the radius of the planet, how big it is. And for reference, I circled Earth right here. So this is Earth's radius with our orbital period of 365.25 days or so. And what I want you to watch is that because of the sensitivity of these two methods to planets that are bigger and closer in, watch where all the initial discoveries are, right there of big stuff that's more close in to its own planet. And in order to get down to Earth, slowly, those planets begin to creep down to Earth. And when you add the Kepler data, this is what you get, right? That's the haul from Kepler. Something like 1,500 known planets and a whole bunch of suspected planets. And now, this is actually creeping down toward Earth, so we found some that are about the same size as Earth and orbit in about the same orbital period as Earth. And actually, that's a lot of observations. I mean, 2,000 planet observations is enough that you can start to do some decent statistics. And that's what we've done. So if you look, for example, and you look at the radius of the planets we're finding, so in this plot, Earth has a radius of 1, and something that's in the bin called 2, that would be 2 times the radius of Earth, and so on. And the number of planet occurrences, right? Here's what we find. So if you look, for example, in the bin of Earth-sized planets, 1 to 1.4 Earth radii, it's something like 0.3 or so. So having 0.3 planets is like having 2.5 kids. It doesn't exactly happen that way, but statistically speaking, on average, okay, there's about 0.3 Earth-like planets for every star that's out there. So you can say some interesting stuff with this information. If you look at the first two bins, 1 to 1.4 and 1.4 to 2, that's just planets between Earth size and twice Earth size. And you add those two bars together, the conclusion is every other star that's out there has a planet on average, right? So there are hundreds of billions of stars in our galaxy. About every other one has a planet. That's amazing, right? And Kepler, its job was to find habitable planets, but it has been this amazing treasure trove of other data. So for example, we find, if we look at our own solar system, our planets kind of lump themselves nicely into two categories. In our inner solar system, we have the rocky planets, Mercury, Venus, Earth, Mars. Then in the outer solar system, we have the giant gassy, icy planets, Jupiter, Saturn, Uranus, Neptune, and really nothing in between. But one of the things we find most commonly among planets sits right in here, okay, in this range. We have no analog whatsoever for that in our solar system. Most of the planets that we have found in the galaxy fit into that size class, and we have no idea what they are and no good analog for them. So there's all kinds of interesting stuff to be done here. But as I said, Kepler's main job was to look for habitable planets. And about 2 years or so ago, we started seeing headlines like this. NASA's Kepler discovers first Earth-sized planet in the habitable zone of another star. So if you think about it, that's actually very specific and particular wording. What is the habitable zone, and why go to the trouble of wording it in this very particular way? Why not just say, NASA discovers habitable planet? Why be so particular about it?
Because we don't know if it's habitable or not. We don't know the atmospheric composition or if it's even rocky or solid. We just know its orbit and its size.
Awesome. Do you want to actually come up and give the rest of the talk? Because that's so that's actually as good an answer as I could give. So let's talk about what the habitable zone is for a minute, right? And why you would go about wording it in this very particular way. It's exactly as you just said. So here's the idea of the habitable zone, sometimes called the Goldilocks zone. The notion of the habitable zone is that there is a distance away from the star that is just right for having liquid water at the surface. So here's the idea. Over there is the blazing hot sun, right? And if I walk closer to it, I heat up. If I walk farther away from it, I cool down. And someplace right in the middle is just right. And just right means I can maintain a liquid environment at the surface. And you notice a couple of things going on in this plot. So on the bottom axis, that's the radius of orbit relative to Earth. So if Earth is 1, anything further out, so 10 is 10 times further away, for example. And on the y-axis, you notice there are different stars. There's a little red one at the bottom. Right where 1 is, that's our yellow sun. And you go up and stars get bigger and brighter. There are many different kinds of stars, right? Some burn very brightly, some burn very dimly. And depending on what kind of star it is, the habitable zone moves in or out. You can imagine that if we're talking about a very small star that doesn't put out a lot of energy, I have to be huddled up much closer to it in order to get the necessary warmth to keep water liquid at the surface. And this concept of the habitable zone sometimes takes some flack from people, right? So as Matt said, I was part of a team to design a mission to Europa. And the interest in Europa is understanding whether it's a habitable environment and ultimately whether it's inhabited. We know there are places, and Europa in this plot would lie out here somewhere, way outside the habitable zone, and yet we think there's a habitable environment there, right, in an ocean beneath a thick crust of ice. So the purpose of this habitable zone idea is not to say where life is possible. It's actually to say where we think we could detect it, and I'll come back to that point later on, but I want you to sort of put that in the back of your mind. The habitable zone is about finding places where life would be possible at the surface. So what can we actually say now? And what can't we say? Right? About the star, we can say a lot, right? Because we're actually looking directly at the light of the star. So we can say how far away it is. We can say how big it is, how much it weighs, what type of star it is. We can certainly measure its light spectrum, right? We can determine its age, actually, by looking at its composition. And all of those things taken together tell us something about its history. We know enough about the physics of how stars evolve that looking at it now and characterizing it well tells us something about its past. Did it have a tempestuous youth? Was it a problem for any planets that might be there, right? Did it give off radiation that would sterilize things? So we can say all of those things about the star. What about the planet? So remember, when we look at this planet, we're not actually seeing the planet, we're seeing its shadow. So there's not a whole lot of information there. So what can we say? Well, we can say something about its orbital period. That's something we can measure directly. We know how long it takes to go around. Right? We can say something about the radius of the planet because we see the size of the shadow that it casts. If we put that together with the radial velocity measurement, this other sort of wobble method of seeing, we can say something about the mass. So now if we know the mass and the radius, we can say something about the density, and the density tells us something, puts some constraints at least on what it's made of. Right? Does it look like us? Does it have a density of 5 or so that suggests it's partly rock and partly metal? Is it light like Saturn? Would it float if you put it in water like Saturn would? Right? Those are constraints that we can begin to place by putting the density on there. And that allows us to say a little bit about its bulk composition. But what can't we say? So we can't really say a lot about its surface or atmosphere composition because we're looking at a shadow. We're not looking at the planet itself. We're just looking at the shadow that it casts. Okay? Which means we don't know whether water is there or how much is there. So a planet could be sitting in the habitable zone. Conditions could be right to have liquid water at the surface, but if there's no water there to begin with, that's not habitable. And that's something we can't tell yet. We don't know whether there are greenhouse gases present in the atmosphere, okay? Because we have no idea about the composition. We don't know if the ingredients for life are there. We don't know how reflective it is, how much albedo it has, okay? Why care about how reflective it is anyway, right? What difference does that make? Actually, it makes a lot of difference because what we're interested in when we look at these planets is saying, what is the temperature at the surface? If there's going to be liquid water, that's where it will be. And we want to make a statement about what the temperature is at the surface. So taking the example of an exoplanet here, what is it that determines surface temperature anyway? Certainly, it's the amount of light that comes in from the star. That's what warms the place up to begin with. But we know when we look even out in our own solar system, you go out and you see Jupiter in the sky or Venus in the sky, you see it because it's reflecting some sunlight back to you. The light you see is not the planet's own light, it's reflected back from the sun. So we know that some light comes into the planet and some is reflected back, and the difference between the two is how much energy the planet absorbs. And as the planet starts to heat up, it generates its own temperature and it starts to radiate some of that energy back out into space. And the balance between how much energy it absorbs and how much energy it gives back out is what determines the planet's surface temperature. But we know from our own Earth that we have gases in our atmosphere that act like a blanket that keeps some of that radiant energy in, right? There's a greenhouse effect that has to do with our atmospheric composition. That's something we don't know yet about exoplanets. All of these things matter. Which of these things can we actually know right now for an exoplanet? That one. That's it. Out of the 4, that's the one. And that's the reason for saying Earth-sized planet in the habitable zone of another star, not habitable planet, because that's something we just can't say yet. So maybe these factors, right, the amount of reflectance and the greenhouse gases and the radiant energy, maybe they don't matter all that much. Right? Who cares? If we look at our own solar system, right, we can say how much they matter. Just take the example of Earth, Venus, and Mars. And if we say that the amount of sunlight that Earth receives is 1, we can look at Venus, which orbits closer to the sun. It gets almost twice as much light from the sun because of its orbit. Mars gets a little bit less than half as much light as we do. But Venus reflects more than twice as much of that light away as Earth does. And so the light at the surface of Venus is actually less, despite orbiting much closer to the sun, despite getting twice as much light to begin with. There's actually less light absorbed by Venus than there is on Earth. Right? And Mars, down here, actually reflects the least light. So it absorbs a greater fraction of the energy that's coming in. But what's really instructive is if you look at the greenhouse effect. So Earth has a natural greenhouse effect that comes from the water and carbon dioxide that exist in the atmosphere, irrespective of what we're doing with fossil fuels. We're making things worse, but Earth has its own greenhouse effect that's actually worth about 33 degrees C worth of warming. Our planet is warmer on average by that amount than it would be if we didn't have those gases in the atmosphere. Venus gets more than 500 degrees worth of greenhouse warming, right? That should be instructive to us, actually. It has that because it has an atmosphere that's 90 times as thick as ours, as abundant as ours, and most of it is carbon dioxide. This is what can happen when a greenhouse effect runs away and gets really serious. That planet is scorching at the surface. Mars has a really thin atmosphere, very little in the way of greenhouse gases, and so it gets like 2 degrees worth of greenhouse warming. So the planets actually kind of align themselves in terms of surface temperature in the order in which you would expect, but Venus is way, way hotter and Mars much, much colder than you would expect if you simply looked at their distance from the sun. So all of those things matter, and they're not all things that we can determine yet. But what we can say is, you know, if we make some assumptions about what things are likely like on those planets, there's probably a zone where we could conservatively say this is likely habitable. And if we take that approach and we apply it to what Kepler has found, this is what you find. So the notion here, this again is something like distance from the sun, except here it's the amount of energy received, kind of a way of normalizing for the size of the star. Right? Here's the type of star based on its surface temperature. Everything in green would technically be in the habitable zone. Doesn't mean habitable, but it's within the habitable zone. And that's actually not bad. I mean, that's, what, a dozen, couple of dozen, something like that? So that's really pretty good. And actually, Natalie Batalha, who I mentioned before, she has a great analogy, a great way of sort of conveying this information. So if you took the Milky Way and you scaled it to the size of the United States, and you asked, statistically speaking, how far would you have to go before you reach the first habitable planet? Right? And suppose you start right here in Berkeley. Right? How far would you have to go to find the first habitable planet? So by show of hands, who thinks you have to leave the state of California? Who thinks you have to leave the Bay Area? Who doesn't want to vote because they don't want to be wrong about it? Actually, on this plot, it's about a quarter mile. By the time I walked to my car in the garage just down the street, I would have reached the first habitable planet. They're abundant, right? They're everywhere in our neighborhood, and that's really optimistic. I mean, that's cool. So statistically speaking, you need to go about 10 light years before you find the first habitable planet. And so if we were to go out about 3 times that distance, so if we go out to a distance of about 30 light years, and we put the sun at the middle of the plot, these are all the stars in our galactic neighborhood. There's about 300 of them or so. There should be, statistically speaking, 25 or 30 habitable planets within that neighborhood. That's really optimistic. I mean, there's real potential to go looking for life on these places. So one interesting thing to notice here, the stars are actually color-coded according to their type, and the most abundant ones by far are the small red ones. So this is something we don't have a very good analog for. We live around a bigger, yellower, brighter star. But by far, something like 90% of the stars in our neighborhood are these little tiny M-dwarf stars that are much less massive, much dimmer, and much cooler than our own sun. So a really important area of research right now is to understand whether those types of stars and planets around them might actually be habitable. So, I mean, this is an optimistic picture, right? We've got lots of potentially habitable worlds. Why don't we just go and look for life there? So at the risk of stating the obvious, I will say that looking for life outside the solar system is way different than looking for life inside it. Okay? Inside it, it's tangible to us. We've sent dozens of spacecraft out to every corner of the solar system. We've actually visited every planet. We've landed in 3 or 4 different places beyond Earth, 5 maybe, right? It's really tangible to us. How many of you know about the Cassini mission? Anyone heard of Cassini? So Cassini was a mission to Saturn. Turns out that the imaging team lead from that mission, Carolyn Porco, she's here visiting in Berkeley this year, and she gave a talk down in my part of the Bay Area a while ago. It was an hour filled with the most jaw-dropping, stunning imagery you can imagine, right? This was one, but there were pictures of movies of storms evolving on Saturn and pictures of waves in the rings and jets of material coming out of the moon Enceladus, right? Just extraordinary pictures that she had to cherry pick from thousands of comparably spectacular images. And those are just the pictures, right? The science was comparably amazing, right? We flew through those plumes of Enceladus. We measured them. We touched them. We know what's in there. That's what you can do when you take a spacecraft the size of a school bus and you load it up with cameras and sensitive science instruments and you let it spend a decade driving around the Saturn system. Okay? Real potential for tangible stuff within our system. But what if what you get is not tangible? What if you get is just some faint little distant point of light, like here? I mean, you guys probably can't even see this, here or here or here. If that's all you get, is that habitable? Is there life there? How do you know?
You know.
So it turns out this one is decidedly not habitable. This one might be in the subsurface and probably was in the past. That one certainly is, and there's actually decent evidence that there's life there right now. But we know that because we've actually visited those places. What if all we got was a distant view from far away? So this picture is actually a modern cousin to a picture that for me is one of the most iconic images in NASA's history. So this is an image taken by Voyager 1 when it was about 4 billion miles from home. And it looked back at Earth. And the tiny little pale blue dot there that you see, that's Earth. So Carl Sagan actually coined that phrase, pale blue dot. Right? Could you say that life was there based on that image? Right? And actually, in this picture, you start to see part of the problem, because it's not just that pale blue dot standing alone against black space. It's lost in that hazy, glowy, whatever that stuff is, right? Turns out to be the sun, right? Bits of the sun's rays coming in. And this starts to tell you what part of the problem is, because you can imagine if you look at a star and its planet from close up, you see them as distinct things. And as you start to move away from them, from your perspective, they get closer and closer until you can't resolve them anymore. And that's a problem, right? You need to be able to distinguish the planet from the star. And if we took the Hubble Space Telescope, which has given us just extraordinary imagery of the cosmos, and we put it on this problem, what would happen? So this is a kind of a notional idea put together by Jeremy Kasdan, the telescope builder, of what would happen if you looked back at Earth from the Hubble Space Telescope. So this is from the distance of Mars. That's actually pretty amazing to me, right? You can still see the Bahamas, where I grew up, right? It's a really well-resolved picture from 100 million miles away. So suppose we move out to the orbit of Uranus, about 20 astronomical units away. You can still actually resolve some stuff. You can see the moon a little bit. You can see the difference between oceans and continents. What if we went 10 times further than that? So the most distant man-made object from Earth is Voyager 1 right now. It's about 130-something astronomical units away. So what if we went further out, right? Earth is still resolved against the blackness of the sky. But if you go 100 times further still, now you see the problem begin to creep in. You see a little bit of light creeping in from the star. And if we move the Hubble out to a distance of 4 light years, so that is the nearest star to us, Alpha Centauri, if someone looked back at Earth with a telescope from there, this is what the Hubble would see. That's the star over there, and the red circle is where Earth should be, completely obscured by the light. So how bad is that problem? If you looked up at the sky, right, and it's 180 degrees from horizon to horizon, the distance between the sun and the Earth at that distance would be about 2/10,000ths of a degree. That's what you have to resolve. And the star is 10 billion times brighter than the planet. So that's kind of a problem, right? I mean, you know, in order to say anything about the planet, we actually need to see its light. Fortunately, the astronomers are smart about this kind of thing, right? They know how to tackle this problem. We have engineers who can gently lower a Mini Cooper-sized rover onto the surface of Mars by lowering it from a hovering rocket, right? Any of you guys see that? That was awesome. So it's a difficult problem. It's not an impossible problem. And I think that this will get solved. And actually, there are several promising avenues for doing this already. And all of them kind of amount to doing this. So if I want to see who's in the back, right? And I've got the light in my eyes from something in the back. I'll sort of put my hand over it in order to make out the people that are in the back. You can do that with a telescope too, right? You can block out the light of the sun by putting something in front of it and try to see the planet beside it. And I'll show you one of these. There are several different ideas that are developing in parallel. I'll show you one of them, because to me it's the coolest. Any of you actually remember the original James Bond movies? And anybody see You Only Live Twice? This totally strikes me as something that would happen in You Only Live Twice, right? So here what's happening is you're unfurling this giant starshade whose job it is to block out the light of the sun. So if you watch, right, here's the part where the evil supervillain holds the world hostage for ransom. So if you watch, this starshade flies in front of the star, and all of a sudden you see the planets resolve. So this thing, just to put an idea in your head, this thing is like half the size of a football field. It's massive, and you fly it tens of thousands of kilometers away from the telescope. And the idea in doing that is, if you have something that's that far away, 50,000 kilometers, let's say, and you move it a few centimeters, that's extraordinarily fine control on how you're adjusting it relative to the sun. So you have really excellent control on doing this like just the right amount to block out the light of the sun. And if you guys are wondering, why does it have that weird flower shape, right? It's not just because it looks cool. It actually turns out that light will bend around things. It diffracts a little bit. And if you put up just a perfect circle up in the sky, light will bend around that still and cause problems. And a lot of effort has been put into designing the edges of that in such a way that that problem goes away. So the idea that you see there, the picture that you see there, that's what's been finally resolved as a solution to this problem of light diffraction. And in the movie that I just showed, when the starshade moves in front of the star, you see something that looks remarkably like Jupiter and remarkably like Earth, right? And you can actually see the cloud bands in Jupiter. It would not be that way, okay? That's an animation. But if we did this right, if we really did a good job of this and look back at our own solar system, this is actually what we might see. So now you see the individual planets of our inner solar system resolved. We're now seeing light from the planet, and the astronomers would jump for joy over an image like that, because light is a lot to work with. Okay? So this is what we hope for if we do the job right of designing telescopes to look at extrasolar planets. So suppose we do get that light. Suppose we actually can see the planet resolved from its Earth. What then? Or planet resolved from its sun, rather. So let's go back to Bruno's last statement. The countless worlds in the universe are no worse and no less inhabited than our Earth. Is that true? Yeah? So we actually have the potential to do this, right? What distinguishes our time, this moment in space and time from all the ones before, is not the question we're asking, it's the ability to answer it in a scientific way, right? So how will we do this? The idea behind it is actually really simple. It's so simple that we can do it as a group demonstration here, okay? So this works best if everyone participates. So here's all I want you to do. Take a breath and hold it. Okay. All right, so several important things just happened. The most important thing, from my perspective, is that an entire room full of people were waiting in breathless anticipation to hear what I would say next. I never get tired of doing that. But there are some less narcissistic things that also happened there. And one is that you changed the composition of the atmosphere. So when you breathed out, the gas that you breathed out was different in terms of its composition than what you breathed in, right? And you did it in ways that actually changed the light that would be emitted or reflected from Earth. And that's what we're interested in when we look at an exoplanet. We're looking for something that can actually change the light that reaches our eyes. That is something that you did. You did it by exploiting an energy source, oxygen plus whatever you ate for lunch, that would be an energy source for anything, anywhere, right? Not specific to you, energy is energy. However, and I'm sorry to be the one to break this to you, what you did just now was a little boring from the perspective of looking for life. And I'll tell you what I mean by that. So this is a whole bunch of statements that are just statements. What I want to try and do in the next few slides is actually back up this idea for you. So when we look at light, a lot of you probably know that what we perceive as white light is actually made up of a whole bunch of different colors of light. And if we take white light and pass it through a prism, right, as did the noted English physicist Pink Floyd, do any of you actually know what Pink Floyd is? Like it occurred to me when thank you for a few of you. It occurred to me when I put this lecture together, there are all kinds of cultural references that probably happened like decades before many of you were born. So thanks at least for a few of you for knowing what Pink Floyd is. Okay. But actually, when we break the light apart, it's not just these discrete colors of violet, indigo, blue, and green, yellow, orange, and red. Okay. It's an entire continuum of color, and no matter how finely you chop that spectrum up, you still would see difference from one wavelength to the next. Right here, it's chopped up into, what is that, 7 pieces or 6 pieces or something like that. You could chop it into 100,000 pieces, and each one would be different from the next. And when you do that, suppose we look at a leaf, right? Instead of looking at the white light that reaches us and passing that through the prism, suppose we look at the light that's reflected off a leaf, and now we pass that through a prism. What you see with your eyes is green, right? If we looked, and now we resolve that light into its components. So here, this is the wavelength of light. So this is blue or purpler light, and down here, this is redder light. Right? This is the part of the spectrum that we actually see in color here. And up here is how much light is coming off. So when we look at this leaf, the higher the value on this axis, the more light is reflecting back to us. So here's what you see. When you perceive green, what you're actually seeing is that a lot of the light that comes in here is absorbed, and a lot of the light from over here is absorbed. So that's actually chlorophyll doing its job. That's chlorophyll harvesting the energy of the sun and putting it to work in biochemistry. And here, where the light is mostly green, the leaf actually reflects a lot of its light there. That's why you see a leaf as green. It's because most of the red and blue light has been taken out, and most of the green light is reflected back to you. And the point of saying that, so I said, you're seeing chlorophyll doing its job. What you see when you look at light is actually chemical information. It tells you something about what the leaf is doing, right? That is true along the entire electromagnetic spectrum. So you probably know that the light we see is just a really small part of the electromagnetic spectrum. Okay, it goes way out in that direction and way out in this direction. So down over here at very small wavelengths, those are X-rays, right, that pass through your flesh and not as well through your bones. And over here, out in that direction, those are microwaves that you use to cook your food. And the point of saying that is that there's a very broad electromagnetic spectrum, and light interacts differently with matter at every point along that spectrum. So there's a different kind of information to be gained by looking at the light and its interaction with matter there. And what I want you to notice here, actually, so I said that the leaf is green because it reflects most of its light here. But actually, if you look at this profile, the most light is reflected here, out in this color that we can't perceive. Okay, so this is further out than red light. This is infrared light now. That's something we can't perceive with our own eyes, but cameras can. So what if you looked at the world through different eyes? Not through our eyes, but through infrared eyes. This is what you would see. The green that we're familiar with as a color that comes from leaves is gone because the single most reflective feature of the leaf is out in the infrared. Right? The world looks remarkably different when we look through different eyes. What if we went further out into the infrared? If we looked through different eyes, we would see that we actually all glow with our own light. Isn't that a nice thought? We're all glowing with our own light. Of course, everything that has a temperature above absolute zero is also glowing. So the podium glows with its own light, and so does the piano. So maybe not that special after all, right? But the point is, there is different information to be gained along all parts of these spectrums. So if I look in this same part of the spectrum out in the infrared, where there's a different kind of chemical information to be gained, a lot of information about molecules in that part of the spectrum. And I apply this to the experiment that we just did, the breathing in and the breathing out. And I made the statement that we changed the composition of the atmosphere in ways that we could see if we looked with the right set of eyes. So I did this experiment, right? This is what the air in the room looked like when I looked through infrared eyes, right? And here again, this is wavelength on the bottom axis, exactly the same kind of plot as I showed you. And this is the amount of light transmitted in this case. So if the light passed perfectly through the air and none was absorbed, I'd get a value of 100. And anywhere I see less than that implies that some of the light energy has been absorbed. Right? So that's what I see. Perfect transmission, and now some of the light is absorbed in this range. And there's some absorbed over here and some absorbed over there. So what's actually happening there is that the carbon dioxide and the water that were just in the room air are absorbing a little bit of that energy. You're actually looking at the greenhouse effect, right? This is the greenhouse effect in action. It's light energy being absorbed by gases in the atmosphere that we don't perceive with our eyes. That's what the room air looked like before. So then I took my deep breath and I held it and I breathed out into the instrument that was doing this measurement, and this is what it looked like afterwards. Certainly different, right? There's a whole bunch more here, and a whole bunch more here, and a whole bunch more here. Okay, so it's certainly different, but it's more of the stuff that was already there to begin with. It's just more water and more carbon dioxide. Okay, and that's why I said that what you did was a little bit boring. Because when the Earth exhales, as it does through volcanoes, what it exhales is carbon dioxide and water for the most part. So you're doing something that was going to happen on the planet anyway, right? And you breathing out isn't much of a signature to distinguish life from its environment. So, and I knew that would happen, right? I knew it was going to be mostly carbon dioxide and water, and I didn't want to be boring, so I tried really, really hard to make this more interesting. So right before I did the experiment, I took a couple of cloves of raw garlic and I crunched them up, right? And I waited a few seconds and then I breathed out, right? And I was really hoping that I would see those garlic odor molecules in the spectrum. They should pop up like somewhere around here, but I didn't. And I guarantee you, you would have had no problem distinguishing what I had done, right? Even the ones of you in the back of the room would have gone like, wow, that guy ate a lot of garlic for lunch, okay? It was very clear that those molecules were there. We just couldn't see them, right? And this raises actually a really important point about looking and using light to say something about the presence of life. So what is it that we're looking for? If I boil it down to its simplest, when we look at the light from these exoplanets, what are we trying to find? So we're looking for things, first of all, that we can see, and that means we're looking for life that is capable of creating planet-scale change. Something really big, right, that will jump out of these features that we see. And we're looking for things that we can't explain by anything other than biology. So if we can imagine any process that makes the same set of features that we're looking at, we can't say anything definitive about biology. So the carbon dioxide in the water that you breathed out, easily made by volcanoes, right? Not a way of looking for life. We need something that is perfectly unique to biology. And that means we need to understand a set of processes that might be happening on a planet about which we know very little. And this is where we have the need for the geophysicist and the geologist and atmospheric chemist and all these other people to come together and put their heads on this problem. Is there anything else that could make that signature that we're seeing? So what is it that makes Earth? I mean, Earth is inhabited. Is there anything that makes Earth look unique from space? So if we look again at Venus, Earth, and Mars, right? Here's Venus up on the top. Venus has an atmosphere 90 times the size of ours, mostly CO2. Boring, right, for the reason I just described. And Mars has a thin atmosphere, but also CO2. Boring, right? Nothing really to be said there. When you look at Earth, that same boring CO2 is there, but also some other stuff, right? Here, ozone, which comes from oxygen, pops out. You don't see that in either of the other two. You see some water there as well. That's interesting, because that's much harder to explain. So what makes Earth appear inhabited from space is the oxygen that we have in our atmosphere. And we tend to take for granted that we have an atmosphere of 20% oxygen, but that actually wasn't always the case, right? About half the history of our planet, we had no oxygen. So how did it get there? Actually from these guys. So these are cyanobacteria, right? They are photosynthetic bacteria. Our plants, who we love to think of as the keepers of photosynthesis, they learned how to do this from these bacteria. Right? These guys were around for billions of years before there was anything like a plant. It is their activity through time that filled the atmosphere with oxygen. So Louis Pasteur, the French microbiologist, said, the power of the infinitesimal can be infinite. These are small. You could fit 1 trillion of them in the palm of your hand. And yet, through time, they took a planet with no oxygen and filled the atmosphere with 20% oxygen. That's what we're looking for. And that's actually the reason for the habitable zone concept. Because only something that has access to the power of the sun, right? In order to do this job of photosynthesis, you need water and you need light and you need carbon dioxide, right? And you need all those things to come together at the surface. So you need liquid water at the surface. That's the reason for the habitable zone concept, not to exclude the possibility for life further out, but to point us toward the places where we actually have a chance of detecting life because it has a big enough imprint on its atmosphere. So let me talk a little bit more about oxygen, because it's kind of instructive. And in the exoplanet world, a lot of the attention gets focused on oxygen for exactly the reason that it is the single greatest feature in Earth's atmosphere that looks like biology. So let's talk a little bit more about this. And I want to ask a few questions. The first is this: is oxygen an obligate product of photosynthesis? Right? We all, when we learn in school this is photosynthesis, that's always sitting at the end of the equation for photosynthesis. So is that inevitable? If a biosphere learns how to use light energy, is it always going to make oxygen? Simple answer, no. Right? So look at this picture. The green guys here, those are the cyanobacteria that I just showed you. They make oxygen during photosynthesis. They use the kind of what we call plant photosynthesis that generates oxygen. And sitting here cozy right up next to them, these are also photosynthetic guys. Don't make oxygen. They actually use sulfur and make hydrogen sulfide as an end product. There are several different kinds of photosynthesis that don't make oxygen at all. So we can't count on the fact that if photosynthesis emerges, it will always make oxygen. We know it won't always be true. And actually, for the 1.5 billion, 2 billion years that our planet didn't have oxygen, right, before these guys emerged, we had life. Would we have known it? Right, without oxygen there? Don't know, right? So actually, this is where some of our research in the virtual planetary lab comes in, some of my research in that group. We have systems that we can use to try to address that question. So what you see here is a microbial mat. So microbial mats, like if you don't brush your teeth for a few days, right, they'll start to get kind of slimy. That's not that I've ever done that experiment, but that's a biofilm of bacteria. Bacteria love to develop sort of films on surfaces. If you let that process go unchecked, there actually are places where you can find growths of bacteria, nothing but bacteria, 5 to 10 centimeters thick. Right? And we have some of those things. We've brought them back to our laboratory, and they are systems that represent almost all of the metabolic diversity that exists on Earth in a pocket-sized ecosystem. So we can do whatever we want to them, right? We can change the atmosphere to make it look like 3 billion years ago. We can change the composition of the ocean, because in their world, the ocean is just a bucket of water this size, right? And we can look at how they communicate with their atmosphere and ask, what is it they're doing? So in this case, it's oxygen-producing photosynthesis, but we can take that away. We can remove their ability to do that and ask, when the world was younger and we only had this other kind of photosynthesis, which is biochemically easier, what happens then? Do we actually make anything that we can see with a telescope? And what happens when it reaches the atmosphere and light starts hitting it and other processes happen? That's where a lot of the active research is in this field right now, is understanding what is possible if you don't have oxygen. Is oxygen a uniquely biological signature? If you see oxygen there, does it always mean that life made it? No. Right? There are actually at least four different ways known of making oxygen in the absence of life. And we don't have to look any further than our next door neighbor of Mars. There's actually oxygen in the atmosphere of that planet. Not a lot, but a little bit. And enough to tell us there are ways of making oxygen in the absence of life, because there certainly isn't photosynthesis on the surface of Mars. Right? Fortunately, for each of the ways that have been identified to make oxygen in the absence of life, there are other things you expect to see in the atmosphere, other gases like carbon monoxide, for example, that would give you a hint that that process is going on. So looking for those other things is a way to kind of get after those false positives. But it means you need to have understood these processes, and you certainly better be able to identify and pick those other things out of the spectrum, and that influences how you design the telescope that you look with. Lastly, about oxygen. Is oxygen emblematic that we are being unimaginative or too parochial? Does anybody know what this is? This is another of these, bless you, cultural, thank you. It's another of these cultural references that I know predates most of you. It's the Horta, right? So this is from the original Star Trek, and the idea was this was a creature made of silicon, and in the background you can see the painted bowling balls. I think those were its droppings, also made of silicon. So this question, could life be made of something different? Really, it sticks like a splinter in the mind of people. I have never given a public talk where someone didn't ask the question, can life be made of something other than carbon and live in something other than water? And Carl Sagan actually summed this up really nicely. He really had a way with these sort of things. He said, there's a famous book published about 1912 by Lawrence J. Henderson, in which Henderson concludes that life necessarily must be based on carbon and water and have its higher forms metabolizing free oxygen. I personally find this conclusion suspect, if only because Lawrence Henderson was made of carbon and water and metabolized free oxygen. Henderson had a vested interest. It doesn't mean that he was wrong about it. It just means that whenever you reach the conclusion that things should be exactly the way they are here, you should go back and question that assumption. Is that necessarily right? Right? And actually some significant thought has been dedicated to this. So the simple answer, the truthful answer is nobody knows. Right? Nobody really knows if life could be made of something different. And the boring answer is it actually doesn't matter all that much when we look for life. Because what we're looking for is not the life itself. If we looked at Earth from a distance and saw oxygen, we're not seeing us and our carbon-based chemistry. We're seeing the products of metabolism. It actually matters more in understanding where to point your telescope in the first place than it does in looking for evidence of life. But I understand, this is a topic that interests people. So there actually has been some serious scientific thought dedicated to this. So the National Research Council, about 10 years ago, put together a panel of chemists and biologists and origin of life people whose job it was to address this question. Could life be made of different stuff? And if you want, they wrote a report. You can go and read all 150 pages of it if this is a topic that fascinates you, or I can boil it down for you in about 12 seconds. Right? They said, if we really try to think broadly about it, right, really let our minds be open, the only absolute is that life requires energy. Everything we understand about physics and chemistry dictates that life requires energy, and that's the only definitive statement you can make. Life is probably made of carbon, so they distinctly said, we really think that life is made of carbon. And life requires a liquid, but there's no fundamental reason to believe that that liquid is water. So that actually echoes kind of a common viewpoint, right? Carl Sagan called himself a carbon chauvinist, but not really a water chauvinist. So he thought carbon probably important, water not as much. And if you had asked me this question 4 or 5 years ago, I would have said just the same thing. Carbon probably important, water, not so important. And this matters because there certainly are places where worlds are dominated by liquids other than water. If we look out to the Saturn system, we have the moon Titan that has lakes and oceans of liquid methane and ethane. Possible. But if you ask me for my 2 cents, right? So I should say, first of all, as a person who likes to believe he has some imagination, I would love it if life was wildly different, right? That there's something just spectacularly different from what we know. If I think about it like a chemist, and I use what I know about the organizing principles in physics and chemistry, I actually think that life doesn't just require a liquid, it requires a solvent. A solvent is something that dissolves some things and not other things. It mediates the interactions among them. And that's what biology is all about. Right? It's the interaction among complicated molecules that confers life-like property. And I actually think that life requires a solvent with properties that are very like or unique to water. So for me, I went from not being a water chauvinist to really being a water chauvinist when I thought about this question like a chemist. Right? And that requirement for solvent actually constrains quite a bit what life could be made of. So there's a colleague of mine, a clever biochemist, who sort of went through the exercise of taking everyone's favorite second choice, which is silicon, right? Silicon life. And he showed most of the kinds of functional structures that life makes out of carbon can conceivably be made out of silicon, right? At least in principle, if you carry it no farther than that. But if you take those things and you put them in water, they either spontaneously combust or they explode, right? So the solvent matters very much. And to me, I have really become a person who thinks that Henderson was probably not far off. Right? Maybe not the metabolizing free oxygen, but the carbon and water part, probably not far off. So, if someday we do everything right, we build the right kind of telescope, we look out, and we see the light from that star and we resolve it, we might see something like this. Same kind of plot I showed you before. It's a spectrum with wavelength on the bottom and reflection on top. Right? And a colleague of mine, Vicki Meadows, who does this sort of work, when she puts this figure up, she puts a caption like, maybe someday, right? If we're all really good and we cross our fingers, maybe someday we'll get something like this. But actually, so if you think about the spectrum that I showed you when we did the breath experiment, comparatively speaking, this is crappy, right? I mean, look at, so all these error bars are a measure of how uncertain, and it's very blocky and chunky. What happened to the beautiful chemical information that I showed you before? So here's the problem. Fundamentally, what astronomers are doing when they look at anything is they're collecting photons and they're sorting them into bins, right? This one has a wavelength of this, and this one has a wavelength of that, and that's how you build up a spectrum like this. But when we look at one of these distant stars, so remember I told you the light from the planet is something like a 10 billionth of the light coming from the sun? Think about looking out at a distance and seeing some faint star on the horizon. That's 10 billion times brighter than the planet that you're hoping to see. So you have very little light and very few photons to collect and sort and put into bins. And that's what generates this error, because fundamentally, the amount of uncertainty that you have really depends on the amount of photons that you can collect and put into a bin. The more of them you have, the more that error goes away, and you begin to have that very nice spectrum like I showed you before. So this requires some really careful choices in what to do, because I could chop this spectrum up less finely, fewer bins, and then each bin would have more photons in it. So for each bin, I'd have a smaller error, but it would be more chunky and blocky, right? Or I could resolve the spectrum much more finely and accept that my error is going to be much bigger. Or I could stare for a lot longer. Or I could build myself a bigger telescope, right, to collect more photons to begin with. So this is the Hubble, right? The Hubble's dish is bigger than I am. It's like up here somewhere, right, from the floor to here, 2.5 meters. The James Webb Space Telescope that will launch in a year and a half or something like that. This is its mirror, right? Collects something like 10 times as much light. So this is what's being contemplated for a life detection mission on planet, something that size or larger. And it's partly for the purpose of collecting a lot of photons in, right, so you can get a better spectrum. But also the astronomers have this formula that they use, right? So fundamentally, your ability to resolve a planet from a star depends on the size of the telescope, right? So here, this theta, that's how fine an angle you can resolve. And you want that value to get smaller and smaller and smaller in order to be seeing planets, resolving planets that are further and further away. This is the wavelength of light that you're looking at. And all I want you to notice here is that that value changes as the telescope gets bigger. The bigger you make D, the finer you can resolve the thing that you're looking for. So fundamentally, building a bigger telescope lets us look further and further away, and it lets us look at more habitable worlds to try to answer that question that we're getting at. So when we look, to wrap things up, when we look out, this is a tiny little patch of sky that was looked at from the Hubble telescope, and everything that you see is a galaxy. There are a lot of stars out there, right? 70 billion trillion stars in the observable universe. And at least for the patches of sky that we've looked at, about half of those have a planet, right? And 10, 20% maybe have an Earth-sized planet or a planet in the habitable zone. That's a ton of places. And we have the potential and the possibility to actually look at those places and answer this hundreds of years old question, right? We know how many habitable worlds there are. We have no idea how frequently life emerges. That is one of the great problems in science. When the conditions are right, how frequently does life emerge? No idea. But we actually have the potential to answer that question in a statistical way, right, by making wise choices about the telescopes we build and about what we choose to look for. And that's what all of this ongoing research is designed to do, to tell us what is diagnostic as a feature for life, what is the background from which we have to fish that signal, how far out should we look, right, to give ourselves a decent chance of finding things. That's where all the research lies now. So I would love to believe that this is actually something that will be possible in our lifetimes. I think it is, right? If we decide, this is something we can decide to do, to have this look and see if life is out there. So thank you very much for your attention. I hope that... Thank you. I hope that I've conveyed a little of what is exciting in this field and what's going on now. I'm more than happy to answer questions.
I have a question.
Yep. Is there life on Mars? Is that the question?
That is my question. Is there life on Mars?
I'll give you the same answer I did before. There's no evidence of life on Mars. Doesn't mean it's not there. It means there's no evidence. Yes, sir.
What is your take on astrophysics
That's a really good question. It kind of gets to this issue of like in our own solar system, stuff is tangible to us, right? We can go out and touch it. And these stars are far away. So right now, Voyager 1, one of my favorite NASA missions ever, is, like I said, 134 AUs away from the Earth, something like that, and it's moving, right? It's going like thousands of miles a second, or it's really going fast. At its current rate of speed, it will take about 80,000 years to get to the very next star. So if we have any hope at all of going further than that and having it take a reasonable time, we need something that's much, much faster than that, right? There's been quite a bit written on that. I mean, there are all kinds of folks thinking about how can you make something go faster, right? So you need particles that are moving much faster. Maybe you can use the solar wind, or maybe you take the stuff that you have on board and you accelerate it really fast, right? So our standard rockets, they burn rocket fuel, that stuff comes out, and that's what propels. If you want things to go way faster than that, you need to find a means of accelerating that material much faster. And I think that's what you're talking about.
Yeah,
Right?
electromagnetic pulsion.
Yeah, so that gets a little bit outside my realm of expertise. But if we were ever to have any hope of leaving our own solar system and doing it in the lifetime of a person, that kind of thing is essential. Whether it can actually be done, I don't know.
Well, it was discovered by a scientist by the name of Carlos Alcubierre,
Mm-hmm.
who in 1991 was challenged that is warp technology possible, and he proved it.
Hmm.
In fact, there was a professor at a conference in Cleveland, Ohio, who showed actual model of a warp drive of contraption, and they laughed at him until he showed them. By the time he showed them, you could hear a pin drop in the conference room. They said it was possible. In fact, NASA is right now, as I speak, is constructing electromagnetic pulse type of warp field for the space travel. So in this case, it would take 6 months for us to get from here to Mars, where this thing will get you there in 12 days.
Hmm.
So it's really exciting right now.
Yeah, they don't tell me about that stuff. Thank you.
When you look for suns, are there specific suns that you look for due to radiation? I mean, like the red ones, maybe need to be closer to those.
I want to ask your question a little bit louder so we can.
Yeah, I'll repeat it, or you can go ahead if you want.
Yeah, when they look for suns, they look for obviously planets orbiting suns, and certain suns give off less light, so the planets need to be closer. But certain planets give off more radiation. So there are specific types of suns that they look for when you look for.
Yeah.
planet orbiting
Yeah, so just in case everyone didn't hear, that's actually a really excellent question. When you look, are you targeting particular kinds of suns? So this is sort of another one of these things where you arrive at the conclusion that the best kind of sun to look at is the one that you orbit, because you know life can be there. That's, again, like it's maybe a little bit narrow-minded. If you go to stars that are much bigger than the sun, stars have different lifetimes, okay? So stars that are very big they live fast and hot lives, and they burn out quickly. And they generate a lot of ultraviolet radiation. And ultraviolet radiation, for the same reason that it will burn your skin, causes problems for life. So stars that are too big are sort of ruled out on that basis. Stars that are small, so remember that plot that I showed of the stars in our local neighborhood? About 90% of them are smaller than the sun, maybe half the mass or less of the sun, which means they're glowing mostly red. They're much cooler, you have to be much closer in, okay? More than 10 times closer in. That's good in a lot of ways, right? Because it means that if the star is less luminous, maybe we'll have more of a chance of resolving the planet. On the other hand, they're closer together. So that makes it more challenging to look at with a telescope. From the standpoint of radiation, there are a couple of things to worry about for these smaller, redder stars. They live for a long time, so that's great. That problem is not there. Their light quality is different. So the kind of light that drives our photosynthesis, there's not a lot of it. Actually, most of it is in the red to infrared, okay, because they're cooler. The other kind of photosynthesis that I showed you, the little purple guys in that diagram, they mostly use that kind of light. So that's probably also not a problem. The thing that a lot of people worry about is these, if you think about not just what the star looks like now, but what it's looked like over the course of its lifetime, these smaller, redder stars have a tendency to be really tempestuous in their youth. Like they generate these big flares of ultraviolet light that would tend to sterilize anything that's there. So that may be a problem. Not only would it sterilize